In this video, we're going to talk about Ohm's law, power, and energy. So the first thing is I want you to understand the importance of Ohm's law and how we apply it in a variety of situations. Also, we'll need to be able to plot Ohm's law on a graph and be able to read that graph. And we're going to, in another video, look at the difference between power and energy levels and how to solve for each. And lastly, we're going to work on efficiency this week and understand how power and energy flow in and out of a system. So let's look at Ohm's law. This is the most important relationship in all of circuit analysis. It applies for DC circuits, which we're working on right now, AC circuits, which we'll get to later, digital circuits, if you're taking a digital class at some point, microwave circuits. It applies over time. That means, for the next hour, if we measured something for an entire hour, it would apply. Or if we look at something right this second, it applies. So Ohm's law applies to every situation and every circuit. So it is the most important relationship that you're going to learn this semester. And we're going to talk about how to apply it right now. Basically, it's the relationship between current, voltage, and resistance in a circuit or at a resistor level or at a component level in any portion of your circuit. So the effect that we're trying to establish is this current or this flow of charge that we talked about last week. The potential difference or the voltage between 2 points is the pressure that we apply to the system to get that started. And then the opposition to that is the resistance that is encountered in the resistor or in a portion of the circuit. So all equations kind of have this relationship where the effect is the cause divided by the opposition. And Ohm's law is no different. The effect that we're looking for is the current. The cause of the current would be the voltage, and we divide by the resistance, which is resisting that flow of current. So there are 3 different ways you might want to write Ohm's law. The way I learned it, clear and plain and simple, V equals IR. Voltage is current times resistance, or current, which again is the previous formula we looked at. Current is voltage divided by resistance, or resistance is voltage divided by current. Remember the triangle formula I gave you before, you can use it here as well. If you're looking for voltage, you just cover that up, and it's I times R. If you're looking for current, cover up current, it's voltage divided by resistance. If you're looking for resistance, it's voltage divided by current. And I've put this in Blackboard for you in case you want to see it. There's also a great tool online that you'll find in many different colors and different fonts. It's called the Ohm's Law Wheel. And basically this tells you all of the equations you can use to find these different properties. So to find voltage, you have 3 equations here. To find resistance, there's another 3. To find current, there's another 3. And to find power, another 3. Now we'll get to power later, and I'll explain how all of these are related after we do. However, you already know that V is equal to I times R right here. R is equal to V over I, and I is equal to V over R. So you already know 3 of these equations, and by the time you've finished with both of the videos, you'll understand where all of the equations came from. And you won't need this necessarily. You can find all of the equations really from 2 very simple relationships, and one of them is Ohm's law. So what are we saying? Here is our basic circuit. Here's the voltage supply you learned about last week. Here's the resistor you learned about before that. And then when we connect the positive terminal of the voltage supply to the resistor, and then the negative of the voltage supply to the other end of the resistor, and we have it grounded in our circuit, this gives our current a path to flow through the circuit. So this E, this electromotive force, is what kicks everything off and starts the process. And since we have a complete circuit, we're going to have current flow through the circuit. The resistor is going to resist that current flow and control the amount of current that we see through the circuit. And that current going through my resistor will lead to a drop in voltage from this point to this point. Remember, voltage is a difference in potential between 2 points. So this voltage drop is the difference in potential from here and here. Just as for the voltage source, the difference from here to here shows is the voltage drop across the voltage supply. Okay, so let's talk really quickly about direction. Remember, we said current flows from the positive terminal to the negative. Whoops, I need to go back. Previous, let's go back and look at this again. Current flows from the positive terminal back to the negative. That's conventional current flow, right? So here, notice that if current flows into the resistor this way, we're going to see a drop in voltage from this side to this side. It takes energy to push that current through that resistor. So we're going to start out with more potential energy here and have less once we get to the other side of that resistor. Or if the current's coming from the right to the left, we're going to see the opposite happen. We're going to see a greater potential over here than over here. So basically, you're at a higher potential on entering the resistor than you are leaving because it takes energy to push that current through that resistor. Okay, so if we have current flowing through our 2 kilo ohm resistor here, and we have a 16-volt drop from this side of the resistor to this side of the resistor, what would our current have to be right here? If you said 8 milliamps, you're correct. Let's look at this problem right here. There was some voltage source here. It's not an open circuit. There's a voltage source there. And it's supplying 1.5 amps of current through my 80 ohm resistor here. So if that's the case, what would that voltage source would have to be? Well, Ohm's law says 1.5 amps times my 80 ohms would give me the voltage, which would have to be what? If you said 120 volts, you are correct. So Ohm's law is V equals I times R. So if you want the triangle version of this, V is equal to I times R. Other ways to write it are I equals V over R equals V over I. So let's work a few problems. We have a CD player that draws 100 milliamps of current when 5 volts is applied. What is the resistance? Okay, so we have that I is equal to 100 milliamps, V is equal to 5 volts, and we're looking for the resistance. So we could just use this equation right here, R equals V over I. Make sure you're using the equation correctly. So we have 5 volts that we're applying and drawing 100 milliamps. So the resistance of the CD player, remember 100 milliamps is the same thing as 0.1 amp, or 5 over 1/10, which is 50 ohms. If you're still having some issues with the scientific and engineering notation, please let me know, and we'll see if we can find some resources to help you with that. Okay, so in problem number 2, we see that we have a current of 10 microamps and a resistance of 3.3 mega ohms. What is the voltage? So we're looking for voltage here, which is I times R. So we have 10 microamps times 3.3 mega ohms. So I'm going to move that up here. So micro is 10 to the negative 6. And mega is 10 to the 6th. So when I multiply this, I get 33 times 10 to the negative 6 plus 6, and that's just 0, right? and 10 to the 0 is just 1, so the voltage drop would be 33 volts. Okay, next problem. We have a 12-volt automobile tailgate bulb and is drawing 6 amperes from the battery. What's the resistance? Resistance is voltage divided by current. We've got 12 volts divided by 6 amperes. There are no prefixes in this, so it's just 12 divided by 6, or 2 ohms is what we have there. And let's work on another Ohm's law problem. We have 120 volts applied to a 200 ohm resistor, and we want to the current. Well, then the current is going to be V over R, where we have 120 volts divided by 200 ohms. And that gives you 0.6 amperes. The correct way to write that in engineering notation would be 600 milliamperes. Okay. Let's work on this problem. We have an electric heater that draws 8 amps when connected to a 120 volt supply. What is the internal resistance of the heater? Well, R is equal to V over I. So if we have a 120 volt supply over 8 amperes, that means that we've got 15 ohms. Now, using what we learned in chapter 2, how much energy in joules is converted if the heater is used for 2 hours during the day? So what we're talking about with chapter 2 there is going back to our voltage equation and our current equation, both using charge, okay? So voltage is energy divided by charge, and current is charge over time. So if we can find charge in this equation, then we can apply it to the charge in this equation. And since we already know voltage and current, and we know time, we should be able to get to that energy right there. Okay, so let's start with our current equation right here. Okay, so I is equal to Q over T. We know that the current is 8 amperes, and the time that we're talking about here is 2 hours. Okay, we're talking about having 8 amps used for 2 hours, and we want the charge there. Remember, this time in this equation is in seconds. Okay, so we're going to have to be careful of that. So Q is equal to I times T. So we have 8 amps and 2 hours. We're going to have to convert that to seconds because in this equation time is in seconds. So I'm going to multiply that by 3,600 seconds in an hour so that my hours will go away, and I have amperes, which is coulombs per second, times seconds. So I'll just have coulombs as my answer. So that's 57,600 coulombs. Now I'm looking for omega up here, and I know the voltage is 120 volts, and now I know Q. So when I solve this equation for omega, I get voltage times charge. So we've got 120 volts times 57,600 coulombs. So the energy in joules that's converted over that 2 hour time period is 6.91 megajoules. Okay, now we need to be able to plot Ohm's law on a graph. So graphs are very important in engineering. A lot of they tell us the behavior of certain components, and you'll be interested to look at those and see how your component's going to behave in your circuit. So plotting Ohm's law is pretty simple actually. For instance, this 5 ohm resistor at 5 volts, if we apply 5 volts to the resistor, 5 divided by 5 is 1. That's 1 ampere there. So that's 1 point. At 10 volts, 10 divided by 5 is 2, so we should have 2 amperes. At 15 volts, 15 divided by 5 should be 3, and so on. And you notice this creates a straight line. So a resistor will give you a straight line. Okay, we will discuss slope at another time, but the slope is actually 1 over the resistance, if you want to remember that. Now for a 1 ohm resistor, that's going to be a much steeper slope because remember the slope is 1 over 1. I clicked the wrong button. And for a larger resistor, we're going to see a much more narrow slope. So 1 over 10 would be the slope for that, so a much smaller slope. You can also use the graph to determine the resistor value. So I can look at not only 15 divided by 3 and figure out that has to be a 5 ohm resistor. I can look at the difference. So the difference in voltage from here to here is 5 volts, right? To go from 15 volts to 5 is a difference of 5 volts. Well, in that 15 to 5, we went from 3 to 4 amps. So the difference was 1 amp here. So the difference of 5 volts divided by the difference of 1 amp is 5 ohms. So we can look at Ohm's law right here at this point, or we can look at it overall and look at a trend and still see the 5 ohms there. Here we see the change in voltage is from 6 to 2 is 2 volts. And from that same point on the graph, we see that that we go from 3 milliamps to 4 milliamps. So 2 volts divided by 1 milliamp. Remember, 1 milliamp is 1,000th of an amp. So 2 divided by 1 milliamp would be, what would that be? 2 kilo ohms. Very good. So let me show you a diode. This is not a device we're going to look at in our class. It's a semiconductor device, and it acts as a low resistance path to current in one direction and a high resistance path to current in the reverse direction. It's almost like a switch. So when the current's going in the right direction, you see that we have very low resistance and we allow all of the current to flow, okay? And when the current is going the wrong direction, we see that we have a very resistive component here that's trying to block all of the current. And that's basically the resistance curve of a semiconductor diode. In the next video, we'll talk about watts.